If users search images with messy natural language, tags alone won't carry it. Clip plus FAISS gives you text-to-image retrieval in Python with a real semantic baseline. This is the workflow you'll know how to run when we're done, which indexes images for semantic matching and retrieves the most relevant pictures for a natural language query. I'm Professor Pine, teaching search and IR with simple Python. Image search breaks down when you rely on brittle tags or manual labels. People type messy queries. They want images that match meaning, not exact words. Clip maps images and text into the same vector space so similarity feels semantic. FAISS gives you fast nearest neighbor search over those vectors. Together, they let you ask plain language questions and return the most relevant pictures at scale. At a high level, we turn every image into a vector and every query into a vector. Then, we measure closeness. If a red circle image and the phrase red circle land near each other, they match. This approach is robust to phrasing and can work over hundreds or thousands of images with low latency. We will build a small, clear pipeline that shows the pieces in action. You will see a single image check, then ranking over a small set, then FAISS exact search, then an approximate index trade-off, and finally prompt ensembling plus re-ranking. That makes the flow predictable and approachable before you scale it up. This snippet computes a single clip similarity score between a toy image and a short text. We load the OpenAI clip model via clip.load on CPU and sketch a red circle on a white canvas using Pillow. The variable IE holds the image embedding from model.encodeImage after applying the clip preprocess. The variable TE holds the text embedding from model.encodeText using clip.tokenize for input formatting. We then apply torch.cosine similarity to measure alignment between image and text in the shared clip space. The printed cosine value directly indicates how well the two modalities match for this simple pair. In plain terms, this is a single yes or no check that the image and the phrase point to the same location in the clip vector space, and it helps you sanity check that the model and preprocessing are working. Next, we expand to rank a small gallery of images against one text query. This example ranks a small image set against one clip text query. We extend the toy data to include blue and green canvases, keeping the earlier red image. The list IMGs is pre-processed and passed to model.encodeImage to obtain batched image embeddings. We encode the query text with model.encodeText, normalize both sides, and compute a score vector by matrix multiplying image features IEF with the text feature TEF. The variable S holds one cosine score per image, and argmax selects the top name from names. The printed label and score reveal which canvas aligns most with the query semantics. This step shows the natural transition from one comparison to many, and how vector math turns into a ranked list of names that you can present to users. Now we'll plug FAISS into the loop to make retrieval efficient for larger galleries. This code adds FAISS to perform fast nearest neighbor search over clip image features. We convert the normalized image embeddings IEF to float32 as X, then construct FAISS.indexFlatIP to use inner product, which is cosine when vectors are L2 normalized. We add all images to index.add and encode a new text query Q with model.encodeText, normalizing it to match the metric. The call index.search returns distances D and indices I for the top two matches. The printed result shows the best image name with its FAISS score, demonstrating a minimal text-to-image retrieval loop using clip and FAISS. This demonstrates that FAISS gives you the same ranking mechanics as matrix multiplication, but in a structure designed for fast queries and easy later scaling. Next, we demonstrate approximate indexing to trade recall for speed. This snippet switches to an approximate FAISS index to highlight recall speed trade-offs. We build an inverted file index with FAISS.index IVFFlat over the same clip image embeddings and train it on X. After adding vectors, we search twice with the same query QV, but vary IVF.nprobe, which controls how many course lists are explored per query. With nprobe set low, search is faster, but may reduce recall and slightly alter top scores. Higher nprobe increases work per query and typically improves recall and score fidelity. The printed pair of scores shows how nprobe changes the return similarity. This part makes the performance choices tangible. Fewer probes mean latency savings. More probes mean more consistent top results. Finally, we combine ensembling and reranking to make the baseline more robust. This example builds a compact baseline by combining prompt ensembling, FAISS retrieval, and exact re-ranking. We create 2 text templates in temps and average their clip embeddings into TE to stabilize query intent. The FAISS flat index returns top candidates via index.search, and we convert indices to a tensor canned. We then compute exact cosine scores S between the candidate image features IEF and the ensembled text vector TE, sorting with arcsort for the final order. Increasing the number of templates can slightly improve robustness at minor cost. The printed top 3 list reflects the final re-ranked matches for the query. This pattern gives you a fast shortlist from FAISS and a precise final decision by recomputing exact similarities. To map this toy example to a real project, replace the 3 canvases with your image corpus, store embeddings in persistent storage, and run FAISS or an ANN service in the backend. Add timing and accuracy checks as you scale. Recap: Clip turns images and text into a shared vector space for semantic matching. Use FAISS to search those vectors quickly and choose between exact and approximate indexes by tuning recall and latency. One caveat: vector quality depends on pre-processing and prompt design, so raw scores can vary with small changes. Wrap punch: a practical next step is to tune the FAISS parameters, specifically nlist and nprobe, to find the best latency versus recall point for your corpus size. If short, practical IR helps, subscribe and watch the IR videos.